Okay. So last class, we briefly talked about atomic bonding, and we mentioned that most refractory materials are either ionic or covalently bonded, and materials with higher charges, smaller atom or ion sizes tend to have higher melting points, which is what we need for refractory materials. So today's lecture and Wednesdays are on crystal structures, and we'll follow that with another lecture on glass. Most refractories, the microstructure consists of crystals, glass, and porosity. So we're going to look at the crystal structures today and Wednesday, and then we'll go over some fundamentals on glass. So today we'll look at crystal structure notation for crystal systems and directions and planes and crystal structures. There are some crystal chemistry concepts which you can use to predict crystal structures based on atomic size and charge. And then we'll start on the crystal structures, single element structures, binary element structures, and then the silicate structures. So atoms bond together, they form distinct geometric arrangements, and that these arrangements repeat to form a crystal structure. And the crystal structure is going to be a function of the type of atomic bonding, and we're concerned with ionic and covalent, the size of the atoms, and then their electrical charge. It turns out there are 7 types of unit cells, and these are the smallest grouping of atoms that you can repeat to form a crystal structure, to build up a crystal structure. So there's 14 Bravais lattices that come out of these 7 unit cells. So there are 14 options for stacking atoms in unit cells. So these are the 14 Bravais lattices. Cubic, there's cubic primitive, and the dots are the atoms. So there's a dot at each corner or an atom at each corner. There's cubic body centered. There's an atom in the center of the cube. And then there's cubic face centered. There's an atom on each face of the cube. Tetragonal, there's tetragonal primitive. Again, the atoms are at the corners. And then there's tetragonal body centered with an atom in the center. There's orthorhombic primitive. Again, it's the atoms on the corners. Orthorhombic base centered. So there's an atom on the opposite faces in the center. Orthorhombic body centered, an atom in the middle, and then orthorhombic face centered with an atom on each of the 6 faces. Monoclinic, and then monoclinic base centered. So monoclinic primitive has atoms at the corners. Base centered has extra 2 atoms on opposite faces. Triclinic, hexagonal rhombohedral, and hexagonal primitive all have atoms on the corners. So those are the 14 crystal structures. And this is just another way of looking at them. Simple cubic, body-centered cubic, face-centered cubic. Simple tetragonal, body-centered tetragonal. Simple orthorhombic, body-centered orthorhombic. Base-centered orthorhombic, face-centered orthorhombic. Then rhombohedral, hexagonal, simple monoclinic, base-centered monoclinic, and then triclinic. So we can put an X, Y, Z coordinate system on the different crystal unit cells. So here are X, Y, and Z. A, B, and C are the length of the crystal cells, and alpha, beta, gamma are the angles between the axes. So if we do that, we have our unit cells that look like this. So we have cubic. Here's our cubic unit cell. Each side, A, B, and C are equal in length, and then alpha, beta, and gamma are all 90 degrees. In tetragonal, A equals B, and now C is different, but alpha, beta, and gamma are all 90 degrees. In orthorhombic, A, B, and C are all different, but alpha, beta, and gamma are still 90 degrees. In rhombohedral, A, B, and C are all the same. Alpha equals beta equals gamma, but none of them equal 90 degrees. Hexagonal, A and B are the same, C is different. Alpha and beta are 90. Now gamma is 120. In monoclinic, A, B, and C are not the same. Alpha and gamma equal 90, but beta is different other than 90. And then in triclinic, A, B, and C are all different, and alpha, beta, and gamma are all different and not equal to 90. So that's the seven Broglie lattices in crystal notation. So there's directions and planes in these crystals, and then there's a notation to describe these. So these are the directions in a unit cell. They're in square brackets, and they're labeled H, K, and L. H is X, K is Y, L is Z. So these are all, the HKLs just represent a direction from the origin to either a corner, an edge, or a face of a unit cell, and it's always the lowest combination of integers. So this is your X, Y, and Z coordination, or H, K, and L. And your sides of this crystal structure are A, B, and C. So a 1, 0, 0 direction starts at the origin. It goes 1 unit in the X direction, 0 in the Y direction, and 0 in the X direction. So this arrow in the X direction is a 1, 0, 0 direction. This is a 0, 1, 0 direction. So 0 units in the X direction, 0 units in the Z direction, and 1 unit in the Y direction. So 0, 1, 0. This one along a diagonal is a 1, 0, 1 direction. So it's 1 unit in the X direction, 0 units in the Y direction, and 1 unit in the Z direction. So it's 1, 0, 1. And this one from the origin to this corner is a 1, 1, 1 direction. So it goes 1 unit in the X direction, 1 unit in the Y direction, and then 1 unit in the Z direction. And then this one that intersects the center of this face, you go 1/2 unit in the X direction, 1/2 unit in the Y direction, and then 1 unit in the Z direction. So it's 1/2, 1/2, 1, but you're using the lowest combination of integers. So you multiply by 2, so it's a 1, 1, 2 direction. So those are the directions in a unit cell. We can also describe the planes in a unit cell. So these are in parentheses, not brackets. So directions are in brackets, planes are in parentheses. So it's H, K, and L. And now these are the reciprocal of the intercepts of the plane with the X, Y, and Z axes. These are known as Miller indices. So this one here is a 0, 1, 0 plane. So for H, K, and L, we have the reciprocal. So it's 1 over a number or infinity. So H is in the X direction. So it's 1 over infinity. The plane does not intercept the X-axis, so it's 1 over infinity. In the Y direction, or K, it's 1 over 1. It intercepts the Y-axis at 1. And then L is 1 over infinity because it does not intercept the Z-axis. So 1 over infinity is 0, 1 over 1 is 1, and 1 over infinity is 0. So this is a 0, 1, 0 plane. This one intercepts the X, Y, and Z axes at 1/2. It's a 1, 1, 1 plane. So H, K, and L are all 1 over 1/2. which is 222, but we're going with the lower integers, so that reduces to a 111 plane. So that's your 111 plane. And this is a 110 plane. So h is 1/1. It intercepts the x-axis at 1. K is 1/1. It intercepts the y-axis at 1. And it does not intercept the z-axis, so it's 1/infinity. So that simply becomes a 110 plane. So that's the notation for directions and planes. So those are the crystal structures and directions and planes. So there are a set of rules that define these crystal structures based on how the atoms make up the structures. So stable crystal structures are those that have the densest packing of atoms. And there's some additional factors to consider. You have to look at the number of atoms, number of bonds per atom. You have to maintain charge neutrality. You have to consider the atomic size. So the radius of the ion is important, and it's also going to be a function of charge. So you got to consider the radius of an ion in a particular crystal structure and bonding directions. Ionic bonds are not directional, but covalent bonds are. So you have to consider the relative amount of ionic or covalent bonding. And as we discussed last week, there's usually a mixture of both in most of the refractory type materials. So we have to look at the stacking of atoms in 3 dimensions. Most ceramic or refractory crystal structures, you're stacking the anions. So they consist of a stacking of anions, and then the smaller cations fit into the interstitial or void positions. So that there's a simple cubic structure, a cubic close packed structure, and then a close packed hexagonal structure. So this is the simple cubic structure. So in this structure, each sphere, and these spheres just represent the atoms, each sphere has 4 adjacent spheres in the plane, 1 above and 1 below. So in this system, and simple cubic structure, the way the atoms pack, you're going to have 48% voids. So here's the first layer in the lighter gray spheres, and then the second gray layer, darker gray, is the second layer. These atoms are right on top of the atoms in the first layer. And then here's your void space. So this void space is surrounded by these 4 and then these 4 atoms. So it's surrounded by 8 atoms. So the interstitial site is surrounded by 8 atoms. So that's simple cubic packing. And cubic close packing, the second layer is placed above the spaces in the first layer, and then the third layer is placed above the first layer. So this is tighter packing. There's 26% voids. So the lightest spheres are the first layer. The slightly darker spheres are the second layer. So this layer, these spheres fit above the void space in the first layer. And then the darkest spheres are the third layer. And they're placed directly above the spheres in the first layer. So when you have this type of packing, you have 2 types of interstitials. You have a tetrahedral interstitial site. So there are 4 atoms surrounding this interstitial site, and you have your octahedral sites. So there are 6 atoms surrounding an octahedral site. So this is also cubic close packed. In this case, the second layer is placed above the spaces in the first layer, but now the third layer is not placed above the previous layer. It's not placed above the first layer. Again, it's 26% voids. So the lightest spheres are your first layer. The ones that are slightly darker are your second layer, fitting above the voids in the first layer. And now the darker spheres are your third layer. It's not above either the first or the second layer, so it's a different stacking sequence. Again, you're creating octahedral sites, vacant sites surrounded by 6 atoms, or tetrahedral sites, these interstitial vacancies surrounded by 4 atoms. So this just gives some detail on the 2 types of interstitial voids. This is a tetrahedral site, and this is an octahedral site. So there's 4 atoms here, and the void in the center is a tetrahedral interstice. And then in the octahedral configuration, there's 6 atoms, and then the hole or void in the center is your octahedral interstice. So this is where anions are going to enter the structure. So these are basically oxygens in an oxide, or they can be chlorine in a halide, whatever. But these are your anions, and then the cations are going to fit in these interstitial sites. And then the last one, close packed hexagonal. The second layer is placed above the spaces in the first layer, and the third layer is placed above the first layer. This again gives 26% voids. So the lighter spheres are the first layer. The second layer is slightly darker in color. They're placed above spaces in the first layer. And then your third layer is placed above the first layer. Again, you're going to create these tetrahedral interstices and octahedral interstices. So this is a better way of looking at these structures from a side view. This is cubic close packed structure. This is close packed hexagonal structure. So these hexagonal layers in cubic close packed are A, B, C, and so on. In the close packed hexagonal structures, A, B, and so on. So that shows the difference in the stacking sequence between these 2 different types of structures. So there's some additional factors in how these atoms stack. You have to consider the number of bonds per atom. That maintains charge neutrality. You have to also consider atomic size and bond directions. So Pauling has made a set of rules for crystals that have ionic or mostly ionic character. These are going to be your oxides and your silicates. So we'll go over these rules. And here's one. The structure is basically determined on how positive and negative ions can be packed to maximize electrostatic attractive forces and minimize electrostatic repulsion forces. So when you have ions with ionic character, they're going to be plus and minus. So you want to maximize the electrostatic attractive forces. But when they come in close contact with the electron clouds, they're going to have a repulsion type force. So this equation describes what I just mentioned here. So this is potential energy versus interatomic bond length. So EV is the interatomic potential energy. And this equation here, the first term is the Coulombic attraction. The second term is the repulsion. So A, N, B, and M are all constants. I guess I didn't mention the size. I think N is usually around 1 and M maybe between 2 and 5. But A over R to the N is the attractive term. B over R to the M is the repulsion term. E is the potential energy, R is the interatomic distance. So if you plot the potential energy versus interatomic distance, you plot this equation, it gives a curve that looks like this. So here's potential energy, repulsion, attraction, and then your interatomic separation, R. So this is a potential energy well. It's asymmetric. R0 is the interatomic separation at absolute zero. That's the minimum in the potential energy well. So materials that have high melting points, which reflect strong atomic bonding, have very deep potential energy wells, and they have high melting points. So if you increase the temperature from T1 to T2 to T3, these arrows just represent the amplitude of vibration. So the magnitude of the vibration of an atom about its equilibrium position. And if you look at the midpoints of each one of these arrows as we increase the temperature, the midpoint is shifting to the right. There's a bigger R value, a bigger interatomic separation. So that's what happens as a function of temperature. And these interatomic separations are increasing. So that's thermal expansion. So a material expands because the potential energy well is not symmetric. If it were a completely symmetric potential energy well, R0 would never change. The midpoints would align and there'd be no thermal expansion. So materials with a very deep potential energy well are your high melting point materials, which are your desirable refractory materials. So Pauling's first rule, coordination polyhedron of anions is formed around each cation. So basically the anions, the negatively charged ions, are packed in one of these cubic type or hexagonal type structures, and then the cations, the plus ions, fill the interstices. So there's three types of interstices: the cubic, the octahedron, and then the tetrahedron. The distance between the cation and the anion is determined by the sum of the radii, and that's also we've noted that's a function of their charge. And then the coordination number, the number of anions surrounding a cation, is determined by the ratio of the radii of the two ions. So this is a stable configuration. So there's 4 anions surrounding a cation. They're just in contact. This one is also stable. The cation is a little bit bigger. This one, where the cation is much smaller than the interstitial position, that's an unstable position. So again, the first rule, a given coordination number is stable when the ratio of the cation to anion radius is greater than some critical value. So here's the coordination numbers, 8, 6, 4, 3, and 2. This is the disposition of ions about a central ion, corners of a cube, corners of an octahedron, corners of a tetrahedron, corners of a triangle, and then linear. And then this is the cation radius anion radius ratio. So if it's greater than 0.732, that's a pretty big cation. It's going to sit in this position, in this, and have a coordination number of 8 anions surrounding it. There are the corners of a cube. The cation is in the center of the cube. So this is cubic type packing. These two are a hexagonal related packing. If the ratio is greater than 0.414, the cation will be in an octahedral position surrounded by 6 anions, so the coordination number is 6. If it's greater than 0.225, now the cation is in a tetrahedron So there are 4 anions surrounding the cation. So the coordination number is 4. If the ratio is greater than 0.155, you have a triangle. The void space is where the cation sits. So the coordination number is 3. And if it's a ratio somewhat greater than 0, a small number, you're going to have a linear arrangement. So here's your cation sitting between 2 anions, and the coordination number is 2. So the ratio of the cations and anions really determines the type of crystal structure. So for reference, I have a couple tables here. This is the ionic crystal radii for when the coordination number is 4 nanometers. So silver +1 has a radius of 1.02 nanometers, and so on. So this is the size of typical ions you'll see in ceramic structures. And then I also have another table for the ionic crystal radii when the coordination number is 6. So now here's silver again +1, it's 1.15 nanometers. And over here, it was 1.02 nanometers. So depending on the coordination number, that's going to affect the crystal size. So those are our 2 reference tables. So the second rule, Pauling's second rule, so in the stable structure, the total strength of the bonds reaching an anion from all the surrounding cations should equal the charge of the anion. So this has to give rise to electrical neutrality. So the strength of an ionic bond is given from a cation to an anion is simply the charge on the cation divided by its coordination number. So a couple examples here, Si+4 is going to be in a tetrahedral coordination. So the bond strength is 4 plus 4 charge divided by 4 for its 4-fold coordination. So its bond strength is 1. Al+3 is in an octahedral site. So Al+3, here's your +3 charge. And then the bond strength equals 3/6, 6 because it's an octahedral coordination. So that reduces to 1/2. So you can write an equation for that. So balancing the charge with this is what this equation does. So the valence on the cation and the bars just equal absolute value divided by the coordination number of that cation has to equal the valence on the anion divided by the coordination number of the anion. So this equation gives electrical neutrality. So here's some ions, their radius for the various charges that they possess, the predicted coordination number, the observed coordination number, and then the strength of the electrostatic bond based on that equation. So depending on the coordination number, the strength of the bonds will vary slightly. So the higher the number, if it's 1, it's the strongest bond. And then this one is, well, 1/12, it's the weakest. So his third rule, Pauling's third rule, stable structures really share corners rather than edges or faces of these different polyhedra, whether it's a octahedron or a tetrahedron. So sharing corners minimizes repulsive interaction between cations. So sharing corners minimizes that repulsion term. So here's a tetrahedron. another tetrahedron, and the bond takes place at the corner. Here's two tetrahedrons. They're sharing a face, an edge, sorry. And then here's the same two units sharing a face. And here's the octahedron units sharing a corner, an edge, and then a face. So sharing corners minimizes the repulsive interaction. So when you put these structures together, they tend to share corners rather than edges or faces. There's a fourth rule. Polyhedra formed about cations of low coordination number and high charge tend to share corners. Again, that minimizes the repulsive interaction between the cations because they're sharing corners. The repulsive interaction between a pair of cations increases as the square of their charge. So the higher the charge, the more repulsive interaction. And the separation of cations within a coordination polyhedron decreases as the coordination number decreases. That's the fourth rule, and there's also a fifth rule. The number of different constituents in a structure tends to be small. So it's really difficult to efficiently pack ions and their coordination polyhedra when you have different sizes of ions. So it's difficult to pack these into a single simple structure. So according to this fifth rule, you can pack ions of similar size and make a complex structure. So these are basically solid solutions. Two ions of similar size can substitute for one another, and usually they have to be the same charge. So these are the valences in this column, relative sizes of the ions, and then different ions that can substitute for each other. So a valence of +1, these are rather large ions, sodium, potassium, rubidium, and cesium. These can all substitute for each other in a crystal structure and form solid solution. Another one here, +2, rather large ions, calcium, barium, strontium, and lead. They can all substitute for each other because they have similar sizes. So solid solutions are possible according to Pauline's fifth rule. So going over the different types of crystal structures, we'll start with a single element structure. And this could be a diamond structure. So each carbon atom is either at the center or at the corner of a tetrahedron. So all the lattice positions are equivalent. Every carbon atom is surrounded by 4 other carbon atoms. This is a very strong covalent bond. So here, these spheres are all carbon atoms. They're the sphere at each corner. There's a sphere at each of the 6 faces, and that creates, in this unit cell, 1, 2, 3, 4 tetrahedral positions. So 1, 2, 3, 4. So every carbon atom is bonded to 4 other carbon atoms, and they're all basically at the corners of a tetrahedron. So strong directional covalent bonding in diamond. And another single element structure is graphite. The carbon atoms are in the basal plane, and they're held together by strong covalent bonds. So the black dots are the carbon atoms. They're these hexagonal arrangements, and that layer is covalently bonded. It's a very strong covalent bond. In that direction, you would have high thermal conductivity and low thermal expansion. The bonds between the basal planes, perpendicular to these planes in this vertical direction, are held together by weak van der Waals bonds. So you would have very high thermal expansion in these directions, or also low thermal conductivity. So that's single element structures for diamond and graphite. The binary element structures, you have two distinct atom types. So you have one cation and one anion. So these are the structure names. These are the general formulas. A is a cation, X is an anion. This is the coordination numbers. So in the superscripts here are the coordination numbers. So this is AX. A is a cation, X is an anion. They're in six-fold coordination. Here's an AX structure in eight-fold coordination. And here's another AX structure in four-fold coordination. And here's another structure, A2, X3, and 6 in four-fold coordination. So the formula, the coordination formula, the packing, we went over these: hexagonal closed pack, cubic closed pack, simple cubic, and then the fraction of cation sites that are actually occupied. So in some of these, all of the sites are occupied, and this is an example here of the octahedral sites for sodium chloride, potassium chloride, lithium fluoride, MgO, refractory material, vanadium oxide, and nickel oxide. All of the octahedral interstices are filled. Simple cubic, cesium chloride, all the cubic sites are filled. But in a material like zinc blende, it's cubic close packed. Only half of the sites are filled. Half of the tetrahedral sites. So ZNS is zinc blende. And down at the bottom here, you have a refractory material, Al2O3. It's hexagonal close packed. 2/3 of the cations are in octahedral sites in this alumina structure. So the formulas, the coordination formula, the type of packing, the number of interstitial sites occupied, and then the different crystal structures. So in these binary structures, the binary structure identifies the number of sites rather than the chemical elements. And when you have a solid solution, that allows for the substitution of the different elements, and usually you're going to have substitution of similar size and similar charge. So simple metal oxides are based on all these closed packed oxygen ion structures with the cations and the interstices, whether it's tetrahedral or octahedral. So basically your oxide refractory materials are a closed packed structure of oxygen ions with your cations in the tetrahedral or octahedral sites. So some examples here: the rock salt structure is cubic closed packed. So your anions are in the cubic closed packing. Your cations are in these octahedral sites. So this cation is surrounded by 1, 2, 3, 4, 5, 6 anions. So examples of rock salt structure, refractory materials are MgO and CaO. And then there's a variety of other elements here. Manganese oxide and iron oxide are impurities you might find in a refractory material. The alkali halides are also in the rock salt structure: sodium chloride, potassium chloride, lithium fluoride, and potassium bromide. So if we apply our equation here to sodium chloride, Na has a +1 charge. It's in six-fold coordination around chlorine. So 1/6. Chlorine has a -1 charge. It's in six-fold coordination. So 1/6. 1/6 equals 1/6. For MgO, Mg is +2. It's in six-fold coordination. Oxygen is -2. It's in six-fold coordination. So 1/3 equals 1/3. So the charges are balanced. In the cesium chloride structure, it's simple cubic. So these are the anions. They're in simple cubic packing. And here's your cation in the center of this cube. So here's the cation surrounded by 8 anions. So it's in eightfold coordination. So alkali halides, cesium chloride, cesium bromide, and cesium iodide fit this structure. So the valence on the cation is +1. The coordination number is now 8. And the valence on the anion, such as chlorine, is -1. The coordination is still 8. So it's 1/8 equals 1/8. So 1/8 equals 1/8. The zinc blende structure is cubic close packed. So the anions are in these open circles. They're in cubic close packing. That would be oxygen. And then the cations are in 1/2 of these tetrahedral sites. So only 1/2 of the sites are occupied, and that would be a zinc for the zinc blende structure. Actually, zinc blende is sulf ZNS. So S would be in the zinc blende structure, the sulfur. So only half of the tetrahedral sites are occupied in this structure. So BeO, ZNS, and silicon carbide form the structure. So the valence on Be is +2. The charge is, the coordination number is 4. And then the valence for the oxygen is -2. Its coordination number is 4, so 1/2 equals 1/2. In silicon carbide, the valence on silicon is +4. It's in fourfold coordination, so 4 divided by 4 is 1. Carbon is -4, and fourfold coordination, or 1 equals 1. Word size structure is hexagonal close packed. The anions are in hexagonal close packing in this structure, the open circles. And then now the cations are again in 1/2 of these tetrahedral sites. So here's a cation, and it's bonded to, here's a better one to look at, it's bonded to 1, 2, 3, 4 anions. So oxide, ZNO, BeO, alkali halide, ZNS, CS, CDS, and then carbides, again, silicon carbide. Silicon carbide is different crystal structures. So for BeO, it's +2 divided by fourfold coordination, and then oxygen is -2 divided by fourfold coordination, 4, so 1/2 equals 1/2. And silicon carbide is +4 for silicon in fourfold coordination, -4 for carbon in fourfold coordination, or simply 1 equals 1. Another binary element structure is the fluoride structure. This is simple cubic. So anions, the darker circles, are in simple cubic packing. They're actually in tetrahedral sites. And then the cations are in face-centered cubic packing. They're in 1/2 of the cubic sites. So this is a more complex structure. So in this case, C, A are the calcium in the large open circles, and F, fluorine, are the darker, smaller circles. So oxides that are in the fluoride structure, thorium oxide, cesium cesium oxide, uranium oxide, zirconium oxide, and hafnium oxide. So ZrO2 is a refractory material. It usually has a small amount of HFO2 as an impurity along with the ZrO2. Fluorides are calcium fluoride. So for THO2, TH is +4. It's in 8-fold coordination. VA would be O2 would be -2 divided by 4 in 4-fold coordination. So 4 divided by 8 is 1/2. 2 divided by 4 is 1/2. So the charge is balanced. And then rutile is TiO2. It's a distorted cubic close pack structure. So the anions are in distorted cubic close packing, and the cations are in the in 1/2 of the octahedral sites. So here's a cation surrounded by 6 anions. It's in an octahedral site. Rutile, different oxides here, TiO2 and MnO2. So TiO2 and MnO2 are impurities, typical impurities in a lot of refractory materials. So the valence on Ti is +4. It's in 6-fold coordination. And then the valence on oxygen is -2. It's in 3-fold coordination. So 4/6 or 2/3 is just 2/3. So 2/3 equals 2/3. And then I'm showing the corundum or alumina structure. It's hexagonal close pack. So the open circles are the anions, and it's in hexagonal cubic packing. And then the dark circles are Al for corundum. So the cations, the dark circles, are in 2/3 of these octahedral sites. So that's the corundum or alumina structure. And this is just another diagram showing the same thing. So Al +3 are the solid circles. And then I have the anions, the oxygens in the A layer, and then the B layer fitting over the interstices in the A layer. And then the alumina ions are in these octahedral sites, but only 2/3 of the octahedral sites are filled. So anions, the oxygens are in hexagonal cubic close packing. The cations, aluminum +3, are in 2/3 of the octahedral sites. So for the corundum structure, examples are Al2O3, Fe2O3, Cr2O3. These three are in refractories. Aluminum and chrome are refractory materials. Fe2O3 is pretty high temperature, but it's an impurity. So for Al2O3, the valence of alumina is +3, its coordination is 6, and then oxygen is -2, its coordination is 4. So 3/6 or 2/4, 1/2 equals 1/2. And then the last type of structure to look at today are the silicate structures. These are tetragonal coordination. So the Si +4 cation is at the center of a tetrahedron, and the corners are the O-2 anions. So each O-2 anion at the corner of each tetrahedron is shared with an adjacent tetrahedron. So SiO2, for example, Si is +4. It's in 4-fold coordination. And then O is -2. It's in a 2 coordination. So 4/4, 2/2, 1 equals 1. So these are the silicate structures. They're the building blocks for a lot of different materials. Here's your tetrahedron. So Si is at the center of 4 oxygens. Here's where 2 tetrahedrons are bonded with an oxygen at the corners. So again, silicon is in the tetrahedral sites. These are shearing corners. And this is SiO4 minus 4, Si2O7 minus 6, Si309 minus 6. And now this is forming a ring by sharing the corners, Si6O18 minus 12. These are forming a chain. These are the peroxenes, SiO3N, and it's 2 minus N is a charge. And then this is a double chain, amphibols, Si4O11 N times, and the charge is 6 N minus. So depending on how they share, how many corners they share, they can have an individual tetrahedron, 2 tetrahedrons bonded together, 3 bonded together. They can form rings, chains, and then double chains. So the orthosilicates are SiO4 minus 4. No corners are shared. So phosphorite, zircon, kyanite, mullite, all refractory materials. Phosphorite is a magnesium silicate. Zircon is a zirconium silicate. Kyanite is Al2SiO5, an alumina silicate. And then when kyanite is heated to high temperature, it forms mullite, an aluminosilicate silicate, Al2Si2O13. So these refractory materials are all orthosilicates, and no corners are shared. So phosphorite, Mg2, SiO4 looks like this. You have 2 Mg plus cations to balance the charge of 1 SiO4 minus 4 unit. So here are 2 cations balancing the charge of a silicon tetrahedron. So there's a continuous placement of Mg plus 2 cations and SiO4 minus 4 units in 3 dimensions. So here's a repeating unit cell. So 2 Mg plus 2 cations are balancing the charge on this structural unit, the SiO4 unit. Pyrosilicates, Si2O7 minus 6, that they share 1 corner. These are very rare structures. The metasilicates share 2 corners. SiO3N, it's minus 2N. Wollastonite is a single chain. That's a calcium silicate. Wollastonite is a impurity that you'll find in the silica refractory where you add lime as a mineralizer, and you primarily have silica, but you have a small percentage of wollastonite. Beryl is a ring structure. Ancetite is a single chain. It's magnesium silicate. Diopside is another single chain. Magnesium calcium silicate. Spodumene is a single chain, a lithium aluminosilicate. This is a low temperature material, but the important property in this material, it has very low thermal expansion. And this one, tremolite, is double chains. It's the calcium magnesium silicate, but it's also hydrated. So in this metasilicate structure, 2 corners are shared. This is wollastonite. So these are chains linked by the Ca plus 2 cations. So here's your Ca plus 2, your silica, Si plus 4, is in the center of the tetrahedron, and then the larger circles here are the O minus 2s. And then when they share three corners, you have a framework structure. This is going to form layers, Si2O5N, and it's minus 2N, albite and orthite, orthoclase and calcium. These materials, unfortunately, are in refractory materials as impurities, and they're all low melting. So they're all undesirable. And when we look at some of these phase diagrams, we get into refractory compositions, we'll point out these types of materials like albite and orthite. So three corners are shared. This is albite. You see your Si tetrahedrons are these triangle shapes. You also have an alumina and a tetrahedron site. So the darker triangles are the silica tetrahedrons. The lighter colored triangles are alumina sitting in tetrahedron sites. And this open circle, the circle with a dot in the middle, across the top here and across the bottom are the oxygens. And Na are all these other light gray circles. So that's a pretty complex structure. And that's the albite layered structure. And then the last one here is silica, SiO2. All four corners are sheared, so it's a three-dimensional structure. And we'll talk about silica in detail in a few weeks, but SiO2 can be quartz, tridymite, or cristobalite. Tridymite and cristobalite are the high temperature forms of quartz. So in order to make a silica refractory, you have to convert quartz to either tridymite or cristobalite. So silicon is sitting in a tetrahedral site. So in this case, the larger open circles are Si and the smaller, darker circles are the oxygen. But every silicon is in a tetrahedral site, and all the corners of the tetrahedrons are sheared. So it's a high temperature, three-dimensional structure. So that's the last slide I have. So we gone over basically the binary and the silicate structures. We looked at how the different anions are packed with basically the cations in the interstitial positions. So these structures make up a great deal of the refractory materials. And we'll continue with the structures next time. And then the following week, we'll go over some basics on glass. So you'll have the different crystal structures that make up refractory materials, the primary phase in most refractories. Again, most refractories also have a glass phase. Some cases, a glass phase is introduced on purpose. Usually it's not. But if it's there, you want a very viscous, high temperature glass. So we'll go over some of the properties of a glass. So thanks again for listening in today, and I'll see you on Wednesday. We'll finish up the crystal structures. Thanks again.
Thank
very
you.
much. Thanks.
Thanks.
Thank you again.